Okay, hi everyone. One last lecture this semester. Concerns kinetics and equilibrium. It's described in a couple places throughout Atkins, but most directly in Atkins 17E. I'm hoping to sort of tie some concepts together and kind of complete the circle. Here's the idea, and you don't actually have to do this, but just follow along. Imagine some equilibrium with A going to B, which was first order in both directions. I'm going to assume that there's initially no B present and derive rate expressions for the concentration of these reagents. And if you do that, here's what you end up with. You lose A if the forward step goes, you gain it if the reverse step goes. Flip is true for B. And so you get these two sets of equations. They're actually a little more complicated to solve than you might expect. Again, they're coupled differential equations. If you want to see some cool examples of this, just Google Lorentz strange attractors. But under certain sets of conditions, we can solve it. And this is one of those. If I were to solve these differential rate expressions, I get something which looks like this. So this is telling me how the concentration of A depends on time. Now, I can take this and derive expressions for A and B at equilibrium. How might I do that? Well, what you do is let time go to infinity. This is telling me how the concentration of A depends on time. If I let that time go to infinity, I will get whatever the equilibrium concentration of A is. And what you might quickly see is that this exponential term is going to go to 0. And what that's going to leave you with is an expression that looks like this. K prime over K plus K prime A naught. And for B, you get the complementary expression, K over K plus K prime. Okay? I can now do an interesting thing, which is to derive an expression for the equilibrium constant. KEQ is products over reactants, so B over A, and I probably should have written it out, but if I take my B term, what you'll see is that all of these constants will cancel, and you're left with this, right? K over K prime. And what this expression allows me to do is to relate kinetic rate constants to the equilibrium constant. Another way that you can get equilibrium constants is to say they are defined by the forward rate divided by the reverse rate. And this might be something that you've seen before in a general chemistry class. The language here is very specific, right? So evaluate this statement. A system is in equilibrium when forward and reverse rate constants are equal. If you think about that for a second, if those are equal, you get 1. It seems a little bit off, right? In fact, that's not right. A system is in equilibrium when the forward and reverse reaction rates are equal. So if I brought this K prime up here and I brought the A equilibrium up here, you would get the forward and reverse rates, right? And so this was our notion of equilibrium. It's not a static concept. There's always changes going on, but they're balanced. So I wanted to give you one example of how this is actually used in a kinetics situation. It's called the Lindemann-Hinshelwood mechanism. This is Cyril Hinshelwood. And these concern reactions of sort of the generic type A going to P. If you wanted some specific example, lots of isomerization reactions are Hinshelwood mechanisms. Okay? So here's methyl isocyanide going to acetonitrile. And for a long time, people just thought this was a simple first order process. A just goes to P. right? And the rate law that you would expect for that is just a simple first order process. What happened was that in the 20s, Lindemann and Hinshelwood observed some unexpected concentration dependence. They went to some new set of conditions and things looked a little wonky. And what they ultimately did was propose this reaction mechanism. Rather than a simple first order thing, what you had was two A molecules which could react to form an energetically excited A molecule. That's what the star represents. And this energetically excited molecule would fall apart and form the products. So it's not a two-step mechanism. And again, the way most people thought about this is, well, if this happened, right, this would have to very quickly fall back and relax back to the ground state. The language for that is we're assuming a fast equilibrium, right? This exists in a fast equilibrium. And if that's true, then the expression that we just talked about would apply, right? Forward and reverse rates are equal. The equilibrium constant is forward divided by reverse. I can solve this for A star, right? I plug A star into step 2 and you get some simple first order reaction. So on the surface of it, this is no different than just a regular A going to P. But if you go through and use a steady state approximation, and I'm not going to do it, if you're bored, you can solve this out. What you will find is that the A star concentration, excuse me, looks like this. I then take this expression for A star, you put it into this, and you get this expression for the rate constant. And this is interesting because it predicts two different regimes. If this term, K minus 1A, is bigger than K2, it will dominate, and what you're going to be left with is a rate law which looks simple first order. Again, if this equilibrium is fast and K1A is bigger than K2, you get a simple first order expression. However, if this term is small compared to K2, what you get is something that looks like a second order reaction, K1, K2, A squared. And in fact, this is exactly what Lindemann and Hinshelwood measured. This is a plot of the observed rate constant. Here's how the observed rate constant is defined as a function of concentration of A. And what you'll see is that if you get to really, really low concentrations of A, the rate constant starts changing. So this is consistent with exactly what you'd expect for the Lindemann-Hinshelwood mechanism. Okay, that's all I got. Thanks for checking out all these videos this semester. I hope that they were okay, and I will see you soon. Bye.